lecture series on differential equations for undergraduate students. Today's lecture is on Euler-Cauchy equations. Till now we have learned how to solve second order linear differential equations with constant coefficients, that is Px and Qx were constant, not the function of x. Of course, we had learned both the methods, that is for right hand side Rx to be 0 and not to be 0, that is both the cases homogeneous equations and non-homogeneous equations. Now, we will learn the method to solve linear differential equations where the coefficients Px and Qx are not constants. So, first we will discuss one special kind of equation which has many engineering applications, that is called Euler-Cauchy equation. What is an Euler-Cauchy equation? An Euler-Cauchy equation is of the form x square y double dash plus ax y dash plus by is equal to 0, where the we see that this is a second order linear differential equation where the coefficient of y double dash is x square, coefficient of y dash is ax and coefficient of y is b. Here this a and b they are constants, but the coefficient of y dash, that is ax, and coefficient of y double dash, that is x square, they are not constant but the function of x. We can change this equation to a linear differential equation with constant coefficient with certain substitutions, and that substitution is in the variable x. So, let us see that substitution. Say x is equal to e to the power t, then dy over dx, that is y dash, would be nothing but e to the power minus t dy over dt, and the second derivative d2y over dx2 will be e to the power minus 2t d2y over dt2 minus e to the power minus 2t dy over dt. Now, if I substitute this dy over dx and d2y over dx in the dy over dt and x as e to the power t over here in this equation, we will get this equation as d2y over dt2 plus a minus 1 dy over dt plus by is equal to 0. Now, we see this is a second order linear differential equation where the coefficients are constants a minus 1 and b, both are constant. So, now we do know that how to solve this equation and we can get the solution. However, the solution of this equation will be a function of y as a function of t. This will be that is y as a function of t, while as we want a solution y as a function of x. So, what we get solution as y as a function of t, we will substitute their t as log x and we will get the solution in the terms of x. There is one alternative method to get that alternative method to solve the Euler-Cauchy equation. See, my equation is x square y double dash plus ax y dash plus by is equal to 0. You see here that the coefficient of y dash is x and coefficient of y double dash is x square. So, if I put y as x to the power m, we would be able to, we think is that it could satisfy this equation. Why? We see that y dash would be m times x to the power m minus 1, y double dash would be m into m minus 1 times x to the power m minus 2. So, if y is equal to x to the power m, this is a solution of this equation. These things must satisfy this equation. So, let us substitute it. If we are substituting, we would get m into m minus 1 x to the power m plus a times m x to the power m plus b times x to the power m is equal to 0. Let us rewrite this equation again as m square plus a minus 1 m plus b times x to the power m is equal to 0. Now, if this x to the power m is the solution of this equation, we want, that is this should not be trivial solution, that is this should not be 0 for all x, and if this is a solution it must satisfy this equation, that is this must be 0. This will be 0 if either x to the power m is 0 or this m square plus a minus 1 m plus b is equal to 0. This cannot be 0, hence this would be solution only if m square plus a minus 1 m plus b is equal to 0. So, we would get, that is this would be a solution if it is satisfied. What it says, this equation which we have got in m, This is called characteristic or auxiliary equation. Let us compare this method with the previous method where we have changed it to the linear differential equation with constant coefficient. In that one, what we have got that equation? We have got d2y over dt2 plus a minus 1 dy over dt plus by is equal to 0. To solve this, we require the characteristic equation. What is the characteristic equation? Characteristic equation would be m square plus a minus 1 m plus b is equal to 0. Now, let us compare what just now we have got the auxiliary equation, that was also m square plus a minus 1 m plus b. So, we have got that characteristic equation for both these methods, we are getting the same, and after that what we will get? We will get the solution as the roots of this one. So, here if we are getting, we would get the solution as e to the power mt kind of things, and here we would get x to the power m kind of thing, and here we have to get the solution in the terms of x, that is e to the power t. I have to substitute as x. So, again we will get x to the power m, and here also as x to the power m. So, that says is both methods will give me the same kind of solutions. So, see how we get the solution. We see the equation is m square plus a minus 1 m plus b is equal to 0. This is a quadratic equation in m. So, of course, it will have two roots of this equation, and the solution would be depending on those two roots, and those two roots are depending upon what we are getting the two roots. So, there would be three cases, the two roots m1 and m2, and we will have three cases. The case 1, when I do have both these m1 and m2, they are distinct and real. The second case would be, that is when this m1 and m2 are real, but they are equal, that is double real root. And the third situation we will have when this both m1 and m2 are complex numbers. So, of course, they would be in pair, that is the complex conjugate roots. Let us discuss the general solution in each case one by one. So, the case 1, distinct real roots. When this equation m square plus a minus 1 m plus b is equal to 0 has two distinct real roots m1 and m2, then the two solutions we would have as x to the power m1 and x to the power m2. These two solutions would be linearly independent. We can check this linear independence using the Wronskian. Do you remember the Wronskian? Wronskian of the two solutions y1 y2 was given as determinant containing the solutions y1 and y2 and their derivatives, that is the determinant x to the power m1 x to the power m2, and the second row m1 x to the power m1 minus 1 and m2 times x to the power m2 minus 1. What will be the value of this determinant? This would be simply m2 times x to the power m1 plus m2 minus 1 minus m1 times x to the power m1 plus m2 minus 1, that is m2 minus m1 into x to the power m1 plus m2 minus 1. Now, this x is not 0, and since m1 and m2 are distinct, they are not equal, this will not be 0 for m1 not equal to m2, that is when they are distinct, these two solutions x to the power m1 and x to the power m2, they would be linearly independent. Hence, the general solution would be c1 x to the power m1 plus c2 x to the power m2. This we have discussed the case 1. Now, go to the case 2, double root. That says is that when we do have this equation m square plus a minus 1 m plus b, this has same real root, that what will be that root? That root would be 1 minus a by 2. So, the one solution we would get as x to the power m as x to the power 1 by 2 1 minus a. Now, to get the second linearly independent solution from here, we will use the technique of variation of parameter, that is we will take the second solution y2 as u times y1 and then we will find out what is my u. So, by doing that technique we would get actually y2 as log x times y1, that is u we have got log x. So, the second solution would be log x into x to the power 1 by 2 1 minus a, and the general solution would be then C1 plus C2 log x into x to the power 1 by 2 1 minus a. So, when this characteristic equation has double root, we do get the general solution is of the form C1 plus C2 log x x into to the power half 1 minus a. Now, the third case, complex conjugate roots. When this equation m square plus a minus 1 m plus b is equal to 0 has complex roots, they would appear in the pairs. That is, let us say one's first root is s plus I t, then the second root would be of the form s minus I t. If these are the roots, then the general solution or the two solutions we would get as first as x to the power s cos t log x and the second solution as x to the power s sin t log x. Again we can find it out, that is, this is the similar kind of thing as we have done with the differential equation with constant coefficients. These will be linearly independent, again you can check it using the Wronskian, and the general solution will be of the form x to the power s c1 cos t log x plus c2 sin t log x, where this your s is the real part in the complex root and t is the imaginary part in the constant in the conjugate this complex roots. So, we have discussed these three cases. Let us do some examples to understand this method and how to solve these Euler-Cauchy equations. Let us do the first example. Solve the Euler-Cauchy equation x square y double dash minus 4x y dash plus 6 y is equal to 0. We will substitute y as function of x to the power m. So, we will substitute y as x to the power m, thus y dash would be m times x to the power m minus 1 and y double dash would be m into m minus 1 times x to the power m minus 2. If we substitute this in this given equation, we get m into m minus 1 times x to the power m minus 4 m times x to the power m plus 6 times x to the power m is equal to 0. Now, rewriting these terms, we get m square minus 5 m plus 6 times x to the power m is equal to 0. So, we will get the auxiliary equation or the characteristic equation as m square minus 5 m plus 6 is equal to 0. We see the factors would be m minus 2 into m minus 3. So, the roots would be m is equal to 2 and 3. We do have two real roots which are not equal, that is real distinct roots. So, the two solutions would be y1 as x square, y2 as x cube. So, the general solution would be of the form c1 x square plus c2 x cube. This is a solution of this differential equation x square y double dash minus 4x y dash plus 6y is equal to 0. We can check that this would be the solution. So, if let us say that checking this for x square, if I take x square as a solution, what will be y double dash? That will be 2. So, I will get here 2x square and y dash would be 2x. So, I would be getting minus 8x square plus 6x square. So, that is satisfying this equation. Similarly, we can check with x cube or we can check with this general solution. Let us do one more example. Example 2. Find the general solution of x square y double dash plus x y dash minus 5 is equal to 0. Again we will go with the same kind of function, that is y is equal to x to the power m, y dash as m times x to the power m minus 1, y double dash as m into m minus 1, x to the power m minus 2. Substituting this in this equation and finding out the auxiliary equation, we would get from here we could see that is auxiliary equation should be m square into a minus 1. So, here a is 1. So, a minus 1 would be 0. So, I would be getting the auxiliary equation as m square minus 1 is equal to 0. Of course, it has two roots, m as 1 and 1, that is double root, m as 1 and 1. Now, this is the second case. So, what will be my two solutions? The one solution y would be x and another solution would be x times log x. We can again check by putting the solutions that they are solutions, and so the general solution would be c1x plus c2x log x. Now, let us discuss one more example. So, example 3. solve the initial value problem, x square y double dash plus 4x times y dash plus 9y is equal to 0 with initial conditions y at 1 is equal to 2 and y dash at 1 is equal to 0. So, first we will solve this equation again by the same method, that is y is equal to x to the power m, y dash as m times x to the power m minus 1, y double dash as m times m into m minus 1 into x to the power m minus 2. Substituting this, we would get m into m minus 1 plus m plus 9 is equal into x to the power m is equal to 0. So, we will get the auxiliary equation as m square plus 9 is equal to 0. Now, we see that this will have complex root, that is m square is equal to minus 9. So, I would have the roots as plus minus 3i. Now, if I compare it with our original one, that is s plus it. So, here the real part is 0 and the t is 3 and we are having the two roots plus 3i and minus 3i. So, what will be our two solutions? Our two linearly independent solutions would be cos 3 log x and sin 3 log x. So, the general solution we would get as y x plus c1 cos 3 log x plus c2 times sin 3 log x. To get the particular solution for the initial value problem, what are the initial values? Initial values are given that the function at value 1 is 2 and the derivative at 1 is 0. So, we get what is y dash x from here, that would be minus c1 sin 3 log x into 3 by x plus c2 cos 3 log x into 3 by x. Now, if the first initial condition is that x is equal to 1. So, here if I put x is equal to 1, what I will get? Log x 1 would be 0. So, I would be getting here cos 0 and sin 0, cos 0 would be 1 and sin 0 would be 0. So, what we would be getting y at 1, we would be getting is c1 and that is given as equal to 2. So, this is what we have got from the first initial condition. In the second initial condition, we do have y dash at 1, y dash at 1, that is here if I put x is equal to 1, we will get this term to be 0 and this term we would be getting as 1 and this we would be getting as 3. So, what we would be getting y dash at 1 as 3 c2 which is given as to be 0, which says is that c2 would be 0. So, we have got the two constant values, that is c1 as 2 and c2 as 0. So, what will be my particular solution? Here we will substitute the values of c1 and c2. So, the solution of initial value problem would be 2 times cos 3 log x. Now, you can check that you can put this solution in the given equation, this will satisfy the equation. Moreover, this solution will also satisfy these two initial conditions. So, thus we have discussed the Euler-Cauchy equation of second order. We have learned that its solution is depending on the roots of its auxiliary or the equation and that there would be arising 3 cases. Now, let us do the practical life application of these equations. So, we will now discuss some application. Linear differential equation with constant coefficients have many engineering applications. Here we will discuss one such an application, which is the second order linear differential equation in mechanical vibration. Here what we are discussing very basic mechanical system, that is called a mass on an elastic spring. This is motion of basic mechanical system. This is mass on an elastic spring and this is called mass spring system. What is this system? Let us first understand this system. We do have an spring, this is an unstretched spring. If I hang a mass of size m on this one, you see this is unstretched spring, I had this is stick to here on the one side and on this side I have attached a mass of size m. This will stretch this string. So, let us say this stretching is S naught. Now, what I will do is that is after this stretching, this is at the static one. So, if I pull this mass little bit downwards and then release it, that is I pull this mass downwards, if I am pulling it again this string will get more stretched one and then if I release it, what will happen? This will go up and then it will go under the motion like this one. That is where we are having is that once I had pulled it down and then left it, it will go in a motion. We want to discuss or we want to find out this basic motion of this spring. So, we would see that is how we are going to model this system. Model this system means we will find out what are the differential equations which are governing this motion. Let us see how we are going to do. So, we are going to setting up this model for this mass spring system. Here we have taken a spring which is which would be going to be the whether it will be compressed or it would be stretched, it will resist it. That is a simple spring. It is attached with one hook on the one side. On the second side we had put a mass of size m. Now, that will give it is a stretching, and this is stretching, let us say is that is this stretch is S naught. Here this is in the, this is not in the motion. Once I had put this mass over there, this will just hang on. This position I am taking is the initial position, this initial position, and then this spring has been, this mass has been pulled down. If it has been pulled down, it will again stretch it, and then when we are releasing it will go to the motion. So, now we will make certain basic assumptions for setting up this motion. The first setting up is that we take that motion should be strictly vertical, that is we are not talking about this kind of motion, we will talk about only strictly vertical motion. We are taking that direction towards the downside as positive and direction towards the upside as the negative. This is the static condition, that is from here initially we are starting, that is when the mass has been hung, that is this initial stretch of S naught we have taken, and then we are pulling it down and then releasing it. So, after time t, wherever this thing is, that is suppose it is here, then this is the displacement from the initial condition y is equal to 0 to at y t at time t. Now, how this system is being governed? Let us see, this system would be governed by Newton's second law. What is the Newton's second law? That says is mass into acceleration is equal to force. What is the mass? Mass is being given as m. Acceleration, since we have seen in the last one, that is y is the displacement. We do know if y is the displacement at time t is y t, then velocity would be y dash t, that is the derivative of y with respect to t at time t, that would be the velocity, and acceleration would be the second derivative y double dash t. So, we have got the mass, we have got the acceleration. Now, what is the force? Let us see the force. The force which is governing this complete system. Let us see. When this is unstretched spring, when a mass m is being attached, it has been stretched. When it has been stretched, it says is there is a force acting upwards, say F naught, which is balancing it. So, this force F naught would be on the upward side, and this is not moving, that is it is balancing the weight of this mass. What will be the weight of this mass? By the Hooke's law, this force F naught would be actually minus k s naught, that is this is against, that is whatever the stretching, this k here is called the spring constant, and we are taking this negative sign because this is on the upward side. This is balancing the weight, weight is m into g. Now, the system is in the static equilibrium, that it is not moving, that says is we are having is F naught plus W, that is minus k s naught plus m g, this should be 0, this is not giving any motion, this force is 0. Now, when it goes under the motion, that says is when we are pulling it and then releasing it. When we are pulling it, one more force, that is it is being stretched again, and what is this stretching one? This is stretching from this initial condition y we have taken 0, now this is stretching, extra stretching is of y, that will generate another force F1, and what this would be, again by Hooke's law, this would be minus ky. Again the sign would be minus, since this force is upwards and the k is the spring constant and y is this stretching at the time t. This is called the restoring force. Moreover, every system does has a damper. If the damping is not there, that is there should be some force which is governing this motion, then this motion will go on forever. We will learn this little bit after. Let us say that damping force is F2, this will again be in the upward direction. This damping force is going to govern the velocity, so that it would reduce it. So, a very good approximation of this F2 is minus Cy dash, that is y dash, that is the velocity, and minus c. This c, this is called the damping constant, and again the sign is minus, since this force will also act upon on the upward side. So, now the resulting force, what would be, this c we are also taking as positive, this k is also positive. The resultant force would be F1 plus F2. So, the total force would be minus ky minus Cy dash. Now, we are ready to get the model of this system, that is by second law of Newton's second law, mass into acceleration is equal to force. Mass is m, acceleration is y double dash, the force we have find it out is minus Cy dash minus ky. That is, we have got a differential equation, m y double dash plus Cy dash plus ky is equal to 0. This is a second order linear differential equations with constant coefficients, since all these are constants. So, this is governing this mass spring system, this equation, and this is a homogeneous one. So, we just say that is what we do get, how to get the solution of this and how this motion we are trying to understand. So, first we will discuss the case of undamped system. Undamped system, that is there is no damping is present, that is the damping constant c would be 0. That is what we would get our equation. Our equation would be m y double dash plus ky is equal to 0. That is the term involving Cy dash, since c is 0, that is not present there. Now, here m and k both are positive. So, we would get what will be our characteristic equation for this linear differential equation, that is m lambda square plus k is equal to 0. Its root would be, of course, since both k and m are positive, its root would be complex one, and those roots would be minus square root of k by m I plus and minus. So, the general solution would be of the form a cos t times square root k by m plus b times sin t times square root of k by m. T here I am taking is the time t, that is I am having the equation in y and t. This is the general solution. Now, let us see that is what this general solution is. Let us see in the graph. This is called harmonic oscillation. Why? You see here we are having is, that is for different values of a and b. So, let us say a is equal to 1 and b is equal to 0. For here I have taken m as 4 and k as 3, that is the spring constant as 3 and mass as 4. Then what we are having is, that is this motion, first this black line, you see this is just going like this one. Now, you see what we are having is, it is starting, the motion is being started, that is displacement is going on, it goes up at a distance, then it goes down with the same distance, then it goes up again with the same distance, and you see the time it is taking between the cycles, that is from here to here, here to here, here to here, the cycle is also same, and it is also taking that the displacement, that is the distance it is covering, that displacement it is making, that is also equal. That is what I said is, when we are not having a damper, the motion will go on forever. So, this will go on forever with equal magnitude. Similarly, if I take my a to be 0 and b is to be 1, then you see is that again I am getting this harmonic motion, this pink kind of line. Again you are having is that the cycle is same the magnitude is also same whether upwards or the downwards, and this will go on. Similarly, for the different values, if a and b I have taken as 1, we are getting is that is the magnitude is differing here, and but cycle is there, different cycle, different magnitude, but it is going on. Similarly, with other values as a as 2 and b as 3, we are getting it again, that is the magnitude is getting higher one, and the cycle is again in the similar manner, the smaller one. And then if I had a as 4 and b as -5, we have got that the magnitude is again little bit higher and the cycle is something is little bit smaller, and we are getting that this will go on, this is never going to down, that is the motion will go on forever. So, let us see another example over here. Here I have changed that mass to be 3 and spring constant k is 5, that is it is more resistant string. Again you see the similar kind of pattern we are having. Again I have taken this a b as the similar kind of thing, that is a is equal to 1, b is equal to 0, that is this first one. We are getting is this motion, then if a is equal to 0 and b is equal to 1, we are getting this motion, and so on. We are having, again we are having is this motion is going on with the equal cycle in one motion and with the equal magnitude, whether upwards or downwards. That is what we are calling it as harmonic oscillation, and without damping this motion will go on forever time. Let us see the damped system, that is when the damping is present. So, first we see what is the equation and the solution, and then we will discuss this motion. So, the differential equation would be m y double dash plus c y dash plus k y is equal to 0. Here this m is the mass, c is the damping constant, and k is the spring constant. This equation will have the characteristic equation as lambda square plus c by m lambda plus k by m is equal to 0. Since this is a quadratic equation, it will have two roots, lambda 1 and lambda 2, and those roots would be of the form minus c by 2m plus minus 1 by 2m square root of c square minus 4mk. That is, we will have one root as minus c by 2m plus 1 upon 2m square root of c square minus 4mk. Another root we would have minus c by 2m minus 1 by 2m square root of c square minus 4mk. Let us rewrite it as in the simplified manner. Let us say this first thing as the alpha c by 2m, and the second part, that is beta, as 1 upon 2m square root of c square minus mk. Then we would have the two roots, lambda 1 as minus alpha plus beta and lambda 2 as minus alpha minus beta. Now, you see in the beta we are having this term square root of c square minus 4mk, that is we are finding out square root of some quantity where this c, m and k all they are constant. So, of course, we will have our roots will be depending upon what is this inside this square root, that is c square minus 4mk, whether it is positive quantity, it is 0 quantity, or it is negative quantity. Accordingly, we would have different roots. So, we will have actually the three cases. The case 1 is when c square is greater than 4mk. In that case, we will have two different roots, distinct real roots, lambda 1 and lambda 2. This case is called over damping. Then second case, when c square is equal to 4mk, we will have double real roots. This is called critical damping. We will learn all these terms why we are calling them. And the third case, when c square is less than 4mk, that is its imaginary part, beta would be imaginary, and that is complex conjugate roots. This we would call under damping. Let us discuss the solution in each case one by one. So, general solution in case 1. Case 1 is when c square is greater than 4mk, that is we would have two roots as minus alpha minus beta and minus alpha plus beta. So, the general solution we would have yt as c1 e to the power minus alpha minus beta t plus c2 e to the power minus alpha plus beta t. Here if this alpha is, we do know is that c by 2m and beta is 1 by 2m c square minus 4mk, where m is the mass, c is the damping coefficient and k is the spring constant. Now, for different values of c, m and k, we will get, so that the c square minus 4 m k is positive, we will get the different roots, and if I do give some initial conditions, so that we get some particular solution. So, we will discuss this case one by one. Here what I have taken some values of c, m and k such that c square minus 4 m k is positive, and initial condition what I have taken is, that is y at 0 is 4, that is it is positive initial displacement. Then we do have the another initial condition that would be governing y dash, that is y dash whether it is, I have defined some values and I am classifying them into 3 parts, that is my velocity, initial velocity y dash is positive, negative or 0. Let us see first case y1. This y1 we are having is here as positive velocity initial, that is y dash 1 is positive, I have taken some value. So, in that case how this motion will go on, initially it has been displaced, that is pulled downwards 4 at 4, then it has been released, it has generated, and with the damping it has generated a velocity, positive velocity. So, we are getting it as, that is it is going little bit up and then it is dying down because of damping. If initial velocity is 0, then it is started dying down from the initially, it has not gone up. When the initial velocity is negative, that is the initial velocity is upwards, then we are having, we could have the two cases. One is, that is it is going down like this one and then it is dying down to the displacement is coming to be 0, or it may happen that it comes to 0 and then it goes to the negative one, that is we are having is this motion upwards, but again it will come up and it will go to the 0. So, if the damping is present, ultimately we will have that our motion would stop and after some time we would go to the 0 displacement. Now, if I take initial displacement to be the negative, that is if y 0 is negative. So, again I have taken a case when y 0 is minus 4. Again with the second initial condition about the velocity, again I have divided positive, negative and 0. Now, if the displacement is negative and my velocity is also negative, that is the last case y 4, this case. So, you see is, that is it is first going down little bit and then coming up and it will ultimately reach to the 0, that is the displacement would be 0. If the initial velocity is 0, it is starting with the negative displacement and the displacement is going up, and that is it is reducing and it will certainly reach to somewhere 0. If initial velocity is positive, we could have again the two cases. One case is, that is it has started little bit, that is the displacement has gone very up like this one, that is reduced certainly, and then the reduction power is little bit less and then we are moving over here. We may have this in this positive case, that is it may go to the 0 and then it cross this line, then it goes to the positive displacement and then it is dying down. So, again we have got that when damping is present, we will not have this harmonic kind of oscillation that the motion goes on forever, rather we would be having is that after some time the motion will die down and their displacement would be 0. Now, let us discuss the second case, that case 2, where C2 is equal to 4 m k, that is beta would be 0 and we will have double root, that is both lambda 1 and lambda 2 they are equal to minus alpha. In this case we do know that the solution would be of the form C1 plus C2 t times e to the power minus alpha t. Alpha is of course our C by 2 m. In this case, if I take some values of C and m such that C square is 4 m k, again I have taken initial condition that my initial displacement y is positive and that is 2. Again with the second initial condition about the velocity, we have divided it into positive, negative and 0. So, when the displacement is positive and velocity is also positive, this is the second case where I am having C square is equal to 4 m k, that is we are having double real root. Again it is going little bit up and then it is coming down. So, of course, after some time it will come down. When initial velocity is 0, it is starting from here, it is going down very slowly, but it is going down. Then when the initial velocity is negative, it is going down. First it goes down very fast, then it is going down slowly and it will go to the 0. It may have another case where it is going down to the 0 and then it is going down to the negative displacement, then it will come up and it will go to the 0. That is, again in this case also the motion will die down, that is the displacement would be 0. After sometimes the motion will stop. Let us discuss the third case. Case 3 is when c square is less than 4 mk, that is the beta is pure imaginary. Let us say beta is I omega star, where this omega star is 1 upon 2m square root of 4 mk minus c square, that is this thing is positive. So, omega star would be positive. In this case, the general solution will be of the form e to the power minus alpha t a cos omega star t plus b sin omega star t. By the trigonometry, we do know that this thing we can rewrite as c times e to the power minus alpha t cosine of omega star t minus delta, where this c is such that c square is a square plus b square and this delta is such that tan of delta is b upon a. Now, we see this is the general solution, that is this is telling us the displacement at time t. This is having e to the power minus alpha t and cosine of something. Now, the cosine of any this cosine function we do know this lies between minus 1 and plus 1. So, what we will have, this motion will lie between minus c e to the power minus alpha t and plus c e to the power minus alpha t. Let us see what kind this motion would be look like. You see here, this is the line c e to the power minus alpha t and this is the line minus c e to the power minus alpha t. Again I have taken this some c and m such that c square is less than 4 mk. You see this motion is actually this one, this is going first, it is starting with here initially and then it is going down, then it is coming up and like this. You see each time the magnitude of the motion you are getting is getting lesser and lesser and afterwards it is going to be die down, it is coming to 0. So, this is what is the motion when we do have the under damping. You see is that is when we had over damping, we had got the motions which are just going down. When we had critical damping, again the motions were just going down, and here what we are having is that motion is going down and up and down and up and then they are dying down, that is they are stopping. So, this is what is called the under damping. So, we have discussed the 3 cases of this differential equation which is governing this motion of basic mechanical system, that is called the mass spring system. Now, it may happen that is this motion is being governed by some force, that is we are calling forced oscillation or resonance. What is this? This says is that this motion is being governed by a force or a force is affecting the motion. That means till now what I was having, that is this was the equation of the motion which was equal to 0, that is this was balanced by balanced equation. Now, what we are having is that this motion is governed by one force called RT, that is now we are having non-homogeneous equation my double dash plus cy dash plus ky is equal to RT. Now, what this RT which is governing this motion, this RT is called input, and what will be the solution of this equation y, that would be called output. This is we are giving is that is sometimes we say is that this is what is the input and or this is what the force is being applied, and this output we are calling the response to this force which is governing this motion. So, this is also called the response. For example, let us take this my RT, that is the force which is governing the motion is of the form f naught cos omega t. This omega is something different. So, f naught is a constant and the force is of this form. You see I have taken this special form, that is cosine function. If you do remember, we have to solve this non-homogeneous equation where this both f naught and omega are positive. then what will have the equation? Our differential equation would be my double dash plus cy dash plus ky is equal to f naught cos omega t. Now, this is a non-homogeneous equation. It has solution which is having the solution of homogeneous equation and a particular solution which is governed with this right hand side, that is called the particular solution, and then the general solution we do have as the homogeneous solution plus the particular solution. So, we do have this differential equation. Its general solution is of the form yh plus yp, where yh is the general solution of associated homogeneous equation my double dash plus cy dash plus ky is equal to 0, and yp is the particular solution. Now, we will concentrate on this yp. If you do see, that is what we are having here is that our RT is of the form f naught cos omega t, that is we are having a special form. So, we will use this method of undetermined coefficient. Do you remember that method? We are having one table which is telling us what is the choice of the particular solution yp. That table is this one. So, here what we are having is we are having a constant times cos omega x. So, my choice of particular solution should be of a times sin omega x plus b times cos omega x. Let us see. So, we will have our particular solution as of the form a cos omega t plus sin b sin omega t. If this satisfies the equation, then it will be a solution. So, we would have to find out yp dash as minus omega a sin omega t plus omega b cos omega t, and yp double dash would be minus omega square a cos omega t minus omega square b sin omega t. We will substitute this in the given equation. The equation is my double dash plus cy dash plus ky is equal to f naught cos omega t. When I am substituting those yp, yp dash and yp double dash, we would get the equation of the form k minus m omega square a plus omega c b, and this whole is multiple of cos omega t, and then we do have a sin omega t and its coefficient as minus omega c a plus k times plus k minus m omega square times b, which is equal to f naught cos omega t. To determine this a and b, we would equate these coefficients. So, what it gives is, that is the coefficient of cos omega t on the right side is f naught and on the left side is this one. So, we get the first equation as k minus m omega square a plus omega c b is equal to f naught, and we do not have any term of sin omega t on the right side. So, we will get the second equation as minus omega c a plus k minus m omega square b is equal to 0. These are the two algebraic equations in two unknowns a and b. So, we can solve it and we get the solution. So, we will get what is the particular solution. Homogeneous equation will give me the solution of yh, and we will get the general solution. Now, we will discuss one special case which is called the damped force oscillation, or which is more generally known in the mechanical engineering as vibration. What is this one? This governing differential equation would be my double dash plus cy dash plus ky is equal to f naught cos omega t. I am just discussing with this special one, that is f naught cos omega t. Associated homogeneous equation would be my double dash plus cy dash plus ky is equal to 0. Its solution, let us say suppose that this equation has complex roots, that is its characteristic equation has complex roots, then the solution would be e to the power minus alpha t a cos omega t plus b sin omega t, where this alpha would be c by 2 m and omega would be 1 upon 2 m square root of 4 m k minus c square. Now, this is what we are writing, and then the particular solution general solution would be of the form yh plus yp. This general solution is also known in this vibration case as the transient solution, and this particular solution y p, this is known as steady state solution. Why this is called transient solution and this is a steady state solution, this we will learn a little later on, and we would actually learn these things with the help of an example. This example we will do in the next lecture, where we would really model a vibration model, and we will see that is how the solution is coming at, how this vibration is taking place, and why we call one thing as transient solution, this general solution, and this particular solution as a steady state solution, how this is a response to the input function. All these things we will see in the help of example, and that example we will go with the next lecture. Today we have learned a special kind of equation called Euler-Cauchy equations. This is second order linear differential equations where the coefficients were not constant, but the function of x. We had learned homogeneous Cauchy-Euler equations, how to solve them. We had learned some application of linear differential equation with constant coefficient. We had learned one special application in the simple mechanical system called the mass spring system, and we had learned when there is no force is governing the motion, both the cases. Damp is that when there is no damping and when there is damping is present. So, we have seen the damped oscillations and we have seen the undamped motion, that is called harmonic oscillation. Now, next lecture we will learn one more system, mechanical vibration. Thank you.